All right, sorry I'm not here in class today. I'll be back tomorrow, and I just want to kind of give you a video to go along with some of the notes for today. I'm not going to completely finish both openers, but I really will take some time to talk about the fundamental theorem of algebra, as well as some solving over here. So let me just get you started on the opener. Just remember that this open circle is the composition circle. So that would be g of h of x. And I prefer to write it this way. You don't have to. But my brain, for some reason, just sees it a lot better. That if h of x is the same thing as 2x minus 1, I can perform that substitution. And what that tells me is that anywhere I see x in g, I'm going to sub in the 2x minus 1 instead. So this is going to become 2x minus 1 squared plus 4. Just be careful. 2x minus 1 quantity squared, that's 2x minus 1 times 2x minus 1. So I'd hit that with the area model and then try and fill in the remaining portion here. For 2 times f of x minus g of x, again, it's just a substitution. F of x is the same thing as x cubed plus 3x squared plus 1. And then you're going to subtract the entire quantity for g of x squared plus 4. I think you're more than capable of doing that, combining like terms, then list your leading coefficient, degree, and name. All right, so I went quickly there because I really do want to talk about what's called the fundamental theorem of algebra. The fundamental theorem of algebra states that you will have n solutions to an n degree polynomial. You don't have to write this down. I'll kind of explain what that means, so it's kind of vague. But if you have a polynomial, you want to look for the highest degree. So like if I look at 2x minus 6 equals 0, technically the degree is 1, even though you wouldn't really have to write the exponent of 1. So that tells me that there's going to be one answer, or one root, I should say. Here's a quadratic. The degree is 2. So that tells me there are going to be 2 roots. Sometimes they're x-intercepts. Sometimes they're complex conjugate pairs. They're values that drive the polynomial to 0. Here, the degree is 3. So we're expecting 3 roots, or 3 answers. All right, so if we start with linear, the good old days, you can add 6 to both sides. So 2x equals 6, divide by 2, we get one solution, x equals 3. Okay. Again, according to the fundamental theorem of algebra, we were expecting one solution. You don't have to do this, but hey, if I subbed in 3 back into the original, 2 times 3 is 6, 6 minus 6 is 0, it checks. For the quadratic, it gets a little bit different. It starts off kind of the same. We're still going to add 6 to both sides. I'm going to solve this with the square root method. So I'm going to isolate the x squared. And then I'm going to square root both sides. And just remember that it's technically the plus or minus root 3. Okay. You can stop there, or you can rewrite it as negative root 3 or x equals positive root 3. There are the 2 solutions. The 2 roots where, because we're equal to 0, crosses the x-axis there. All right, for this one here, it's a degree 3, so we're expecting up to 3 answers. You have a couple different approaches that you could take. I kind of see a GCF here of 2x. And we're essentially going from standard form to factored form. And I'm going to set each expression here equal to 0, just like with the zero product property. So here, divide by 2, not too bad, x is 0. Over here, you'll have to add the 3 to the other side, and then square root both sides. And so we get 1, then 2, and 3 answers here. So x equals 0, x equals negative root 3, or x equals positive root 3. Those are the 3 roots. They're all real, so they would be x-intercepts. to that equation there. All right, so how do we solve a polynomial like this, knowing that it's equal to 0? The first thing that you kind of want to look at is what's the largest exponent that's showing? So this is a degree 5, which means I need to see 5 answers for this to be considered correct. So first line of defense, is there a GCF? They all have at least one x. So I'm going to factor out the x. And we saw this on Friday, but if you want to do a u substitution or kind of go right to the area model with the x to the 4th minus 8x squared minus 20. So let's see. So we need two numbers that multiply to negative 20 and add to negative 8. I think it's going to be minus 10 and 2. Yeah. So again, like on the diagonal here, we get the minus 8x squared. So this can be rewritten as x times x squared plus 2 times x squared minus 10. Unlike Friday, you have to keep going and solve for x by using zero product property. So I'm going to set each expression equal to 0. So x equals 0, x squared plus 2 equals 0, and x squared minus 10. Right. And hey, we don't have to work too hard for the first one. X equals 0, that's x-intercept and also y-intercept that passes through the origin. Here, we're going to subtract the 2 from both sides. And when you square root a negative, just remember that the square root of negative 1 is I. So let's call this so x would be plus or minus root 2i. Or you could do plus or minus I root 2. Okay. The I is not on the inside of the square root there. So I'll put both. X equals plus or minus I root 2. So again, here's one answer. Because of the plus or minus here, that's 2 and 3. And then over here, I'm going to add the 10 to both sides, square root both sides. Root 10 can't be broken down any further, but there's plus or minus again, so there's the 4 and 5th solution. So we get x equals 0, x equals negative I root 2, x equals I root 2, x equals negative root 10, and x equals positive root 10. By the fundamental theorem of algebra, we've shown all 5 roots, some are complex, some are real, that would drive the polynomial to 0. When you get to this one here, my advice would be to factor by grouping, but first get everything on one side set equal to 0. Have a great day, and I'll be back in class tomorrow.